Oh, how's it guys? Sorry, just had a quick technical issue. So we just looked up the corresponding value in our z tables that corresponded to 1.2. We found that that value was equal to 0.3849. Remember, as previously discussed, we wanted values greater than. So we've just looked up the sum of those values, but we want that. So how do we get there? 0.5 minus 0.3849, and that is equal to 0.1151, I think. Yeah. Okay. Awesome. So that is the probability that our x bar will be greater than 4, because you want greater than that. We looked up where the value of 4 is corresponding to this mean. So this normal z, or the z value that we looked up, corresponds to our standard deviation and mean, and of course n as well. And we find that for values greater than 4, the probability of the mean being greater than 4 is 0.1152. Okay, awesome. Cool. Okay, so that was part A. We now have part B. Part B goes, the sample mean x bar of the sample of 60 months was calculated and found to be 1.98. So remember what we have here. This is the population mean. We've now been given a sample mean, the sample of 60. So we now have an x bar. Right, x bar is equal to 1.98% per month. Assuming we were not told the population mean, find a 95% confidence interval. So I mean, what our confidence interval finds, or tests rather, not really tests, but it gives us some information based on our sample mean. If we did repeated samples, we'd find that in this range, 95% of those samples, sorry, let me start over. Poor wording. So if we did this confidence interval, right, and we got our sample mean many times, so we did repetitive sampling, right, and we did our confidence interval at the 95% each time. We did this many times. We'd find that 95% of all of our confidence intervals, which we've done many times, the true mean will be in those confidence intervals 95% of the time, the true mean. So we find this 95% gap wide, but that doesn't really tell us much about whether the mean is in there. What the confidence interval tells us, if we have many confidence intervals, is that in 95% of those confidence intervals, the true mean will be present. Okay, awesome. So we've got our x bar. What is our formula for confidence interval? Sorry, struggling to say. X bar plus minus the z value times standard deviation over root n. We have our standard deviation, we have our n, we've got our x bar. We might just need to look up the z value. But so what kind of z value have they given us? They've given us a 95% confidence interval, 95%. Okay, awesome. So we have 1.98 plus minus. And if you recall from, oh no, sorry, there's a different type. Let's look this value up. Okay. Okay, so we're going to be looking up a 95% confidence interval. Maybe just to draw a little graph to help you understand. In essence, because we have our standard normal tables, we want the bottom 2.5% and the top 2.5%. So when they say a 5% level, the 5% level, or the 95% confidence interval, they want to make sure that the center section contains 95% of all the information. So we have to find the 2.5% value. Okay, and so we look up for the 2.5% value. Remember, will be because it's 2.5%, so let's write down, and we're talking about greater than, we have to do 0.5 minus 0.025, and that's equal to 0.4775. Sorry, 0.475. Yeah, okay, awesome. So that's what we're going to be looking at. So we have, looking through the numbers, 0.47, we want a 5, well, we've got 70, we've got 7132. Okay, perfect, 0.475, and that corresponds to 1.9, 1.96. Awesome. So there we go. We have our Z value. Awesome. So let's start on a fresh page. So we've got x bar plus minus Z over root n. We've got x bar is equal to 1.98. We've got sigma is equal to 12 from previous. N is equal to 60. And our Z value is equal to 1.96. And so what we're going to have x bar, 1.96 plus minus 1.96, so 1.98 plus minus 1.96 times 12 over root 60. And that should give us let's figure this part out first. So 1.96 times 12 divided by root 60 is equal to 1.98 plus minus 3.0. Let's round to 4. Okay. And so what we end up with, we then take 1.98 plus, let's start with the lower, so minus 3.04. We end up with negative 1.06. We take the upper, 1.98 plus 3.04. End up with 5.02. And there, that is our 95% confidence interval. And we've used the tables to figure that out. So nice and straightforward. You can have lots of these in the tests and in future weeks. So yeah, very good. Awesome. Okay, so we now have a question. Question 2. Assuming a population standard deviation is 6 and the required level of confidence is 98%, so I'm going to write down what goes is equal to 6. We've got this required rate of confidence. I'm going to maybe put that down as Z for now, 0.98. How large a sample is required? So we don't know what n is. How large a sample is required in order to estimate the population mean with a margin of error L not exceeding 0.8. So L is equal to 0.8. Now these questions, you're going to get at least one in the test and at least one in the exam. Essentially all you need to do is just apply the formula. And you'll find the formula on page 181. I'd highly recommend learning it off by heart because it is free marks. So we have sample size n required to achieve desired accuracy L when variance is known. And what we have, n is equal to Z times sigma over L squared. They've also given us some Z values, so quite nice. So maybe remember that. So the 98% is 2.33. Okay, awesome. So what are we going to do? We're just going to pop it straight into our formula. N is equal to Z times sigma over L. If I'm correct. Yeah, I've done that right. And then squared. We've got 2.33, because remember the 98% was 2.83, times 6 over 0.8 squared. And what we're going to do, we're going to put this into our calculator. Times 6 divided by 0.8. Just put this all in brackets. We're going to square it. And we end up with 305.37. Now, what do you do with all these questions? Always round up. Always round up. The reason we do this is because the number 306 includes, going back to the question, how large a sample is required in order to estimate the population mean with a margin of error L not exceeding 0.8. So because we don't want to exceed this margin of error, we're going to have a bigger sample. In all instances, round up. That's what in this course at least. Okay, awesome. Nice, straightforward. You just apply the formula, and you'll get your marks. Awesome. Okay. Now doing question 3. So you've got to assume the percentage return of a share in any month is a random variable with a mean of 2.2%. So we have a mean, I'm going to put this down as mu for now, 2.2, and standard deviation of 1.9. The performance of a share is classified as bad if the average monthly return over all the months in a year is lower than a certain level C. So we don't know what C is. C is equal to question mark. Find C if 33% of the years are classified as bad. This will also take a bit more of advanced thinking, because does it mean less than is bad or greater than is bad? Of course, we're going to think about, so 0 to 0.33 is equal to bad. So we're going to be looking at less than. You may assume a 12-month year, so you've got an N is equal to 12. And now what are we going to do? So we know the probability of X bar being less than C is equal to 0.33. Well, this is the value they've given us. That is equal to, remember, if we find our Z being less than C, C being this mean or this value that we want to look up, 2.2 over 1.8 over root 12. And so now to figure out what C is, we're going to have to work backwards. We're going to have to find out what the Z value that corresponds to 33% is. Before we do that, let's have a look at our little graph. Remember, 33% of the shares are bad. We're talking about this 33% over here. The tables give values over here. So what value here do we need to look up to get this value over here? 0.5 minus 33%, whoops, 17%. That's what we're going to have to look up. We're going to have to look up the 17% value. So we can do that. If we go straight into our tables, we look for the 17% mark. Oh, we've got exactly at 0.44. So 0.44.